I'm and I will be talking today about our measurement study of POSIX abstractions in modern OSes. Before jumping into our presentation, I'd like to share with you a story that motivated this work, and here is how it goes. So, some time ago, a colleague of mine passes by my office and he asked me, what do you think about running iOS applications on Android devices? And my response to him was, that's very interesting, but it's also very difficult. After some brainstorming, we remembered POSIX. And what is POSIX? Is a set of traditional OS abstractions that are fundamental for portable application development. Therefore, our initial insight was that we can support the translation of iOS calls to Android at the POSIX layer. And given the fact that both Android and iOS are Unix-based and they implement similar POSIX functionality, we hypothesized that supporting the translation at the POSIX layer was a reasonable choice and that it would be relatively straightforward, especially compared to Unix to Windows compatibility efforts. Unfortunately, our life was a little bit more painful, and one of the sources of our pains was the fact that modern applications are using platform-specific graphics libraries, and it is almost impossible to support the translation at the POSIX level. Well, the good news is that although the implementation of the graphics libraries is closed source and their interfaces with the kernel do not follow any common standard, the application-facing API of graphics libraries and the applications is very well defined, and basically, by inspecting the symbols exported by IOCT, iOS, OpenGL, we were directly able to find matching symbols for Android graphics libraries and invoke them. In other words, by elevating the level of abstraction at which we intended to support the compatibility from low-level POSIX abstractions to newer, higher-level abstractions closer to the applications, we were able to build our systems. And also, there have been similar efforts of other people who, by leveraging newer, higher-level abstractions closer to the applications, they were able to build all sorts of exciting systems to support, for example, application migration across heterogeneous devices and other systems. Hence, we believe that there is a wide audience of people, including developers, researchers, and standard bodies, who will benefit from an in-depth understanding of the evolution of traditional abstractions in modern OSes, and by an understanding of the ways in which modern application workloads are using traditional abstractions and identify the needs of modern applications. To support this goal, we built a measurement study around a set of questions, and I will specifically talk in my talk today about 3 of them because we are a little bit pressed of time. And these questions are as follows. First, we will ask which POSIX abstractions are unpopular for modern applications. Second, we will ask which POSIX abstractions are popular for modern applications. And third, we will ask, is POSIX missing any functionality potentially? And we will answer these questions in the context of 3 modern OSes, Android, iOS, OS X, and Ubuntu. And we will use typical client-side applications, popular applications, and we will run common user workloads, such as posting a Facebook picture, sharing a tweet, initiating Skype video calls, and others. Our measurements will consist of 2 different types. We'll first have static analysis that can tell us at large scale which POSIX calls are linked by the application, by the native libraries of applications, and we answer this question at large scale by analyzing the full corpus of more than 1 million Android applications and more than 70,000 Ubuntu packages. And second, we'll have dynamic measurements which can give us, which can answer questions about what POSIX abstractions are invoked by common workloads. And we do that by instrumenting the standard C libraries and analyzing the traces of 45 Android and Ubuntu applications and 10 OS X applications. So since I have set up our motivation and our methodology, I'll directly start with our first question, which is which POSIX abstractions are unpopular for modern applications. And the way we define unpopular is basically which POSIX abstractions are not linked by the native libraries, and therefore if they are not linked, they are not used. We'll answer first with this graph, which shows you the static analysis of our Android applications. On the x-axis, you have 1177 POSIX functions defined by the POSIX API. And on the y-axis, you see the percentage of linkage of the native libraries of Android applications. The first observation from this graph is you can see that there are few very highly linked abstractions, such as memcpy, malloc, and memset. But the very interesting observation here is this long tail of a plethora of unused interfaces. First reason why we have this long tail of unpopular and unused interfaces is the fact that Android is moving away from traditional IPC mechanisms, and it only implements 32% of the defined functions, and it explicitly omits implementing shared memory message queues. It partially implements other abstractions such as pipes and semaphores, and very few applications are linking towards named pipes. Second, in Android, file system is only partially implemented again. 76% of the defined interfaces are implemented, and it's interesting that it specifically misses implementations for asynchronous I/O and database management support functions, and that very few applications are linking towards file logging functions. So the takeaway from this graph, what we have observed is that although POSIX defines a plethora of APIs, there is a huge tail of unused abstractions, and that's already alerting. And we were interested in asking the same question in the context of Ubuntu packages. Again, the same graph shows you exactly the same information. On the y-axis, the linkage of packages to POSIX, and on the x-axis, you have the POSIX functions, and you can observe that the pattern is similar. You have a long tail of many unused and therefore unpopular interfaces. So the takeaway from the answer to our first question is that there is a large number of unpopular abstractions, and there is a departure from traditional IPC and asynchronous I/O functions, especially in Android, which is surprising if you consider the fact that Android applications are highly asynchronous and they manage all sorts of data. Therefore, that naturally leads us to our second question, which is, we have found that POSIX already contains a huge portion of completely unused APIs left in some dusty corner. So what is popular? What are applications using? And we'll answer this with our dynamic analysis on 45 Android applications. In this pie chart, you see the percentage of invocation, you see the categorization of some abstraction subsystems such as memory, threading, and other subsystems, and you see the percentage of invocation this subsystem accounts for. Of course, the distribution is not uniform. That's not really a big surprise given the fact that modern applications are heavily based on memory and threading abstractions, for example, like malloc, memset, and protect, and threading operations for TLS. But when our question gets more surprising and interesting is when we pair the graph of invocations with the distribution of the time dedicated to these abstractions. And here you have a very interesting observation. You can see that IOCTL, which is just a single call, it accounts for more time than most of the abstraction subsystems. And the reason why this observation is very significant comes if we step back a little bit and think about what exactly IOCTL is and why people are using this function. So some background here. IOCTL is an extension API which was implemented in order to help developers implement in the kernel support for functionality missing from the POSIX. In other words, developers are resorting to this function when they want to implement functionality that cannot be expressed from POSIX well-defined APIs. And that's very interesting, and that irritated us to go back in our traces and analyze exactly what kinds of libraries are heavily invoking IOCTL. So you have an extension API which is used to support some missing functionality. The natural thing to do is see who is using this call in order to extrapolate what functionality might be potentially missing. And in this table, we summarize the results of our analysis and across 3 different OSes. You can see that IOCTL in Android is used heavily for graphics and binder IPC, which, as our previous speaker said, is a traditional and a core IPC primitive in Android. You can see that in Ubuntu, IOCTL is used for graphics and network operations, and that in OSX is used for some network operations, and basically that's it. Therefore, in the question which POSIX abstractions are popular for modern applications, the obvious answer is extension APIs. And given the nature of extension APIs, the third natural question is, okay, then what exactly is the functionality that POSIX is missing? And we will be answering this question, starting first by graphics, and remembering here that POSIX explicitly omits support for standardization with respect to graphics interfaces. And that, if you remember our initial challenge of supporting the translation from iOS to Android application, that was exactly the reason why we faced one of the reasons why we faced huge challenges, because there is no standard interface, there is no standard OS interface for graphics libraries to the OS kernels, and therefore developers resort to opaque IOCTL data operations and vendor-specific APIs, which has led to extensibility challenges. The next abstraction that has evolved a lot in the context of modern operating systems is IPC, and we'll start with Android. You saw in the previous table that binder IPC, which is the new core abstraction for IPC in Android, is heavily dependent in IOCTL. And the reason for that is that they're using basically IOCTL to implement a binder driver in the kernel and express some new functionality. And the interesting thing is that besides Android, also Mac, OSX, and Ubuntu have their own IPC primitives. For example, OSX uses Mac IPC, Ubuntu uses DPass and KDPass. And here comes the interesting question of, okay, they have defined all these new IPC primitives, but what happened to the traditional IPCs like pipes from the good old days? Why they don't use that? What's the motivation behind re-implementing things? So, to answer that and shed some light, we ran some benchmarks across the 3 different systems. We took open source benchmark for Mac IPC and binder, and we adapted them to be customized for pipes and Unix domain sockets. And we examined the latency on the y-axis as a function of the transaction size on the x-axis. We run these benchmarks on our consumer devices, on our tablets and our laptops. And the first observation is a clear limitation of traditional IPCs with respect to the latency. So the latency basically is a scalability bottleneck for larger transaction sizes. And therefore, they had to do something new. And this new was to implement newer IPC mechanisms with in-kernel support for zero and single copy functionality, which performed near constant time with the transaction size. So that explains the reason why they had to transition from traditional IPCs to circumvent some limitations and re-implement newer IPC primitives. The last abstractions I will examine here is threading, and the reason for that is the fact that there is an evolution also with respect to the way that threading abstractions were perceived by application developers and are being used today. Basically, the transition has to do with the fact that modern applications are heavily graphics oriented, and therefore they require a main UI thread and a very low latency main UI thread, and that has led to an evolution of the traditional asynchrony paradigm to something new, which is an event-driven programming model. Basically, the dispatching of events is what modern applications are interested in, and that has led to different but yet similar APIs across the 3 OSs, Android, Ubuntu, and OSX, which expose higher level abstractions for thread pool and event loop management, and OSX basically has Grand Central Dispatch to meet the needs of the application developers. So to summarize the answer of our third question of whether POSIX is missing any functionality or not, we have observed that graphics is a functionality which is not standardized and therefore missing from POSIX. We have found out that there is an evolution of the traditional IPC mechanisms to handle limitations, and there are new threading APIs exposed to applications that match the new event-driven programming paradigm. Therefore, I hope I have convinced you that there is some evolution from the good old days when POSIX used to be a very well-defined interface with which applications were interacting to request core OS services, and that was good. We were all happy. Even Ken Thompson has said that the major good idea with Unix was its clean and simple interface: open, read, and write. Unfortunately, given the transitions I have described, in our days the situation looks a little bit like this, where we have multiple layers of software frameworks with which applications interact, and that had led us to multiple challenges and evolutions of the traditional APIs. And our contribution to alleviate a little bit this new scenery was tools and methodology for static and dynamic analysis of modern application workloads. We identified what POSIX abstractions are popular, unpopular, and which ones are missing. And because our study is focused to client-side applications, we are open sourcing our tools, and we hope that others will adjust them to run measurement studies on the platforms of their flavor. And as a last takeaway, I think that it may be important that we, as a community, could revisit some core OS concepts such as IPC, threads, and graphics, given the clear evolution that I've described today. And that concludes my talk. I'm happy to talk with you.